Test.
Okay. Yes, we are live. Welcome to SmolTALK. This is actually the first episode of a podcast dedicated to deep tech and the fascinating people that work with the technology of tomorrow. So my name is Magnus Andersson. I'm CEO of Smoltek Nanotechnology Holding. Today I have the pleasure of having Dr. Farzan Ghavanini as our first guest to this podcast. Welcome, Farzan. I'm really happy to have you here. And please tell a bit about yourself.
Yeah, thank you, Magnus. And I'm also very excited about this, the new Smoltek that we are going to have going forward. So, yes, so I have a Bachelor of Science in Electrical Engineering, and I have a Master's in Microtechnology from Chalmers University. And that was exactly when I started to work with semiconductor processes here at Chalmers University in the clean room. And then after I finished my Master's, I directly started my PhD working with carbon nanofibers, going from microelectromechanical systems to nanoelectromechanical systems. That was a lot of fun, and that was the time I was supposed to make devices during my PhD with carbon nanofibers. And I actually ended up developing growth processes for carbon nanofibers. It was a lot of fun, and many of those ended up later on in different growth equipment. So it was a very good experience. After that, I started working at Chalmers Industry Technique. My responsibility there was to bring new carbon technology, graphene, nanotubes, nanofibers, being developed at Chalmers to Swedish industry, to Nordic industries. And that was mainly work with carbon nanotubes and graphene then. After that, 2015, I started working at fingerprint cards here, a couple of 100 meters away.
When did you do the PhD? Was that back in before the working for the industry consortium?
Yes. Yeah. So it was. I finished my PhD in 2011, and I started working at Chalmers Industry Technique at 2012.
The reason for asking is that there is a link from your PhD thesis into what we do today.
Exactly.
So that's why.
No, that's absolutely right, and we can talk about it later. But then at FPC, I was a fingerprint cards. I was responsible for expanding the product portfolio from capacitive fingerprint sensing to other modalities, including ultrasonic and optical. And then in 2022, April, I started here at Smoltek as the CTO.
Yeah. So it's been a journey then, from growing up in Iran, and now you're CTO of a nanotechnology company in Sweden.
That's correct. That's correct. It's sort of coming back to where I started, and that's what brought me here.
Yeah.
When I Shafiq, who started this company, did his PhD right before I started mine.
Yeah.
So I started where he left off.
Yeah.
Under the supervision of the same professor, Professor Peter Ennexon.
Yeah.
And so I always had a close relationship, I was talking to Smoltek people and to Shafiq to what's going on. And that what they did was really interesting. Over the first 10 years, Smoltek was really working on exploring ideas.
Yeah.
What can we do with this great thing?
Yeah.
And then I think around 2018, 2019, they found this application, a capacitor application, which was very interesting. And then there was a change in the management. They brought in a lot of money.
Yeah.
And that was around the time that I thought, well, this is interesting. Yeah. I want to participate at that. And I had a lot of experience from before. So I joined the company in 2022.
Yeah, I think one of the very special things with Smoltek is that, we're soon actually turning 20 years old. It's quite an achievement as a company still developing. But we have the original founders still more or less on board. I mean, Shafiq is working in the company, and you've been around since your PhD then in closely related areas. And Peter Ennexon, he's still involved as as quite an active shareholder. So
correct.
I don't think there are that many companies that have been, working for 20 years and still have, let's say, the founders that actively on board. So I think it's a unique trait, and I think that's maybe the testament to the potential in the company. Well, anyway, if you look at our technology, what is so special about it?
Right. So carbon nanofibers have two things that really distinguishes them from other material. So they are excellent conductor of electricity at the same time as they are excellent conductor of thermal energy. So and SmolTAK over the years have really worked on these two aspects, combined with the fact that carbon nanofibers are nanostructures, and nanostructures have a lot of surface compared to the volume they consume. So surface to volume aspect ratio is very high.
Yep.
So what we do in capacitor, the reason we are building a capacitor with them is because of exactly that high aspect ratio. Our sister company does the same thing, exploit the same fact for another application, for making electrolyzers a lot more efficient, building on the fact that they are electrically conductive and they also have a lot of surface to volume ratio.
Yeah.
And over the time in the past, SmolTAK has also worked on thermal properties, building very efficient thermal conductor, which at the same time also electrical conductors.
Yeah.
So this aspect ratio combined with very good thermal and electrical properties makes this material very unique.
Okay, so we're focusing on capacitors, and to be more specific, ultra-thin capacitors.
Right.
And that's where we see our edge. And can you elaborate a bit on our technology versus other technologies there, and how you would, so to say, position this technology?
Right. So so you mentioned ultra-thin capacitors. So this is a new and emerging type of capacitors. So ultra-thin capacitors are those capacitors that use they use semiconductor processes, wafer processes, to fabricate capacitors. And they are very different from conventional or traditional capacitors that are using conventional fabrication technology. MLCCs, tantalum capacitors, they're conventional capacitor technologies, and they usually are made not below 300-400 micrometer thick. But now you have the ultra-thin technology coming in and exploiting the semiconductor processes, and you could make a capacitor which is below 100 micrometer thin. We have shown ourselves that we can make a capacitor that is only 40 micrometer thin. Because of their size, they have a number of advantages that have become increasingly more important over time, especially now.
Yeah. And talking about what's happening now, I mean, we can read almost every day about big investments going into data centers and high-performance computing, AI, and so on is kind of defining our time. And some people are talking about the next industrial revolution and so on. Do we have a role to play there?
Yeah, for sure. So ultra-thin capacitors are going to be very important for AI application. And the reason for that is that think about the latest GPU from NVIDIA. We have H100 system, we have H200 system. They have massive transient currents. So it means that they can swing hundreds of amp within nanosecond, right? So you cannot just connect a system like that to your power source. It just collapses because they cannot provide a sudden surge in current.
Yeah.
Current is electrons.
Yeah.
So this means that you need to have access to a lot of electrons very fast.
Yeah.
And a capacitor is a reservoir of electrons. So you need a lot of electrons, means you need to have a capacitor that has a very high capacitance density. And you need it fast. That means that this reservoir should be connected to the point of consumption in a way that it has very low parasitics on its way. And it is placed very close. If it's far away, it takes time for the electron to get to the processor within nanoseconds. So two things: high capacitance density, large reservoir, proximity to the point of consumption, very small in size, that enables you to place it very close to the point of consumption. And these are the two things that ultra-thin capacitors in general, and our technology in particular, offers to this very fast-growing market. The power delivery solution, the power delivery dilemma of these AI systems is something that we will see that will generate a lot of innovations over the next years.
Very good. And also, I guess since we can build the capacitors extremely thin and small, we can also take part of a miniaturization of electronics. That's also like a trend in general.
Correct. Right? That's another driving factor for ultra thin capacitors. So your watches, your AirPods, your wearables, they also need capacitors. And in many of those applications are space constrained. So you cannot use any capacitor. That's a smaller drive compared to AI, HPC, and the more advanced power delivery networks, but it certainly is a drive. There's also other applications. For example, radio frequency application. There you have another need. So you have transmission lines, and these transmission lines are designed for certain frequencies, and they are very small. And you have electromagnetic waves that are propagating on your transmission lines. So the components you use in those transmission lines should be comparable in size to the transmission line itself. Otherwise, you will have reflections. Otherwise, you will have a waste of energy there. So these ultra-thin capacitors, like our capacitor, becomes very important. These high-frequency applications like RF and optical as well.
Very interesting. And I guess they're also for radars and stuff like that, where you need lots of energy and high frequency.
Those applications are also, I think, the KPIs of ultra-thin capacitor match very well with the requirements of those applications.
And then what are the main technologies then to realize ultra-thin capacitors, and how do we fit in there?
That's a very good question. There are two main technologies out there. There is one silicon trench capacitor technology, and the other one is our technology in principle. There is also a third technology that is called ultra-thin MLCCs. There is a niche product out there. Not everybody has it. Some companies offer that they manage to sinter this ceramic powder into very thin sheets so that they can make these ultra-thin MLCCs. They have certain disadvantages. They don't have very good thermal stability. The capacitance drops over at higher temperature pretty fast. They have a voltage derating at higher voltage. And you cannot create this mapping of contact points that you have usually on ultra-thin capacitors made with silicon and our technology that matches that of CPUs. You cannot do that with MLCCs. But when it comes to silicon trench capacitor and our capacitor, we are both exploiting the same structural advantage, so to say. Silicon trench capacitor and our technology, we both make 3D structures. They make those 3D structures by digging holes and trenches in silicon. We make those 3D structures by growing nanofibers. And with that, we create a lot of surface that can be used for making a high capacitance density capacitor.
So I guess if we look at where we stand today, we have a new technology, as you said, growing fibers instead of digging trenches. And then it's like offering a new S-curve in performance and innovation, right? Where we have been digging trenches for quite some time, and this is the new technology where we can, grow the fiber so that we can increase performance over time to get to new levels, right? If I understand
Correct,
right.
Yeah, absolutely.
Yeah. If we look at our CNF-MIM technology, and what can we say distinguish it from other technologies in terms of technology aspects?
Right. So I think that's a question that we receive most often, how our technology distinguishes itself from silicon trench technology, right? Yeah. And I think that's a very important question. And to answer that, we need to take a closer look on how these two are made. I just mentioned that in a silicon trench, you dig trenches.
Yeah.
So these trenches, in the most advanced capacitor out there today, if you divide the depth of the trench to the width of the trench, we refer to it as the aspect ratio of the trench, you get a number around 20-25. This number, this aspect ratio, is what is the parameter that tells you how much capacitance density you will get with that technology. In comparison, what we make, we are growing in Gen 1 right now, we are growing fibers that are roughly 50 nanometer in diameter, and they are 5 micrometer in length. That gives you an aspect ratio of at least 100. So this 100 aspect ratio compared to 20 translates to an advantage of capacitance density. But the guys making silicon trenches, they cheat a little bit, right? So when they deposit, so they make the trench, they deposit the first layer of metal and then dielectric and then the metal. You get your first capacitor. But they don't stop there. They continue.
And they do this with ALD, right? So
yes. Yeah. So they repeat that 4 times. Yeah. So layer after layer after layer. So in principle, they are selling you 4 capacitors in one package. Normally, it's not a problem. But you would notice the problem when you look at the method it's used, as you said, ALD, to deposit those layers. ALD is atomic layer deposition.
Yeah.
It's a slow process because you deposit layer by layer your structure. So slower process translates to lower throughput. That's higher cost. So we know from our calculation that ALD is the major cost of building our capacitors. Now they have 4 of that. It doesn't translate 4 times higher, but it significantly increases the cost.
Yeah.
So you could see that now we get comparable performance with the big advantage on the cost side in our technology, because thanks to high aspect ratio that we get, we only need to deposit this ALD layers once, not 4 times. And that's how we exploit today the advantage over aspect ratio. But this is only Gen 1.
So it's comparing apples to apples. We have 1 ALD and they are 4, right. So it's a cost advantage.
Exactly.
Everything else equal.
Exactly. And going forward, we're not going to stop at 5 micrometer tall fibers. As you increase the length of the fibers, your aspect ratio increases.
Yeah.
We want to get to 10 and 20 micrometer tall fibers. And then there is no way, even with multiple layers of a stacking, you would be able to rival that type of capacitance density.
No.
That's one. And then you have another important aspect. As I said, that this parasitics in an AI application or in applications that you have current surges becomes very important.
Yeah.
So our bottom electrode is the carbon nanofiber. As I said, they are excellent electrical conductors.
Yeah.
And that means that translates to very low ESR, which is very difficult for a technology that dip a trench and deposit a very thin layer of metallic ALD to rival. So, and the last but not least is the fact that we could grow these fibers on any substrate. We are not limited to silicon. And we have not exploited this, and this is a long-term plan, but certainly we will, when the volumes are very high, we don't need to limit ourselves to expensive silicon substrate. We could use glass substrate.
Yeah.
We could use aluminum foils. We could use ceramic substrates. So that's a flexibility that our technology has.
And the cost of our fibers, it's not that relevant in the context, right?
So you could ask me, so how do you calculate the cost of growth? And then again, I said that this time.
Yeah.
How fast you could grow the fibers.
Yeah.
And the growth rate of fibers is very high.
Yeah.
We have a plasma-enhanced chemical vapor deposition, and thanks to the presence of plasma and the high temperature, you grow these fibers super fast. Yeah. So it's a fast process.
Yeah. So, apples to apples today, even though we have perhaps another fruit than an apple, but it's comparable performance, but then, much bigger potential in the future.
Yes.
This new S-curve that we basically offer.
Exactly. Yeah. It's not as easy for silicon trench capacitor to increase their aspect ratio. They run into a number of other issues, which we don't.
Yeah. Now we're in a phase where we go from lab to fab, as we say, and which means that we're going to the market and we're trying to industrialize, or we are going to industrialize our capacitor. So what are the main milestones for us to have a commercial breakthrough?
The technology that we're developing is new. There is nobody else doing anything like that out there. So when you do something new like that, reliability becomes very important.
Yeah.
Because people out there, they do not have any point of reference. So you need to prove that your technology is fundamentally reliable. So this is one of the major milestones in front of us.
Yeah.
And that is exactly what we are working on. And recently we have also published a press release showing the success we have had lately on proving that the carbon nanofiber-based technology to build capacitors is fundamentally reliable. We put our capacitors into a thermal chamber. We cranked up the temperature to 85 degrees and waited for 1,000 hours in principle. Yeah. And we saw that there's almost nothing happens to them. We had some failures, that one capacitor specifically died, but these are the things that we can remove in advance. There are early failures, there are infant mortalities that you could develop a process, that you could screen your capacitors, and we are at the earliest stage of that. But the most important thing here is that we showed that our technology is fundamentally reliable. And that is one important aspect that we need to show to our customers, to potential customers, before we could do any commercialization, that these are reliable.
Yeah, and I would think that normally you think it's a great advantage to be unique, but the flip side of that is that you have to prove it, since you're the first one doing it, right?
Yeah,
so
exactly.
The burden of proof is bigger for us.
Absolutely, yeah. Absolutely. Yeah. And we had already shown in the lab that these guys are working well, but it's another thing. Working in the lab is one thing. Working under operational conditions, harsh operational conditions, is something very different. Yeah. And this is where we have worked a lot, and we are spending a lot of our resources. The other aspect is, of course, performance.
Yeah.
So we don't need to show that we are the best in the market, but we need to show that we have the performance that we make in the lab, which is comparable with competitors. We can make that on samples that we could share with our potential customers. They can go and measure themselves and see for themselves how they perform, because there are some KPIs that we provide, but probably they want to integrate that in their own system and get to know more about it. So, and this Gen 1 that we talked about is exactly addressing that. It aims at providing these the samples for showing performance at customer sites. So I think if we show the performance is okay, and if we show they are reliable, then we have a lot of data that we have collected in the lab that shows we could already achieve very high capacitance density. We had another press release we published lately that we showed we have achieved more than 1 microfarad per square millimeter. Yeah. And we know we could do that, right? So, but first we need to show that the basic functionality and the basic reliability. And I think these are the two important things we need to achieve before we are in a commercial phase.
Yeah. And also, I think it's worth here to talk a little bit about our partners. And recently, we were invited and chosen by ITRI as one of, I think, 3 partners to go to the exhibition and the big, one of the world's biggest semiconductor fairs in Taiwan.
True.
So just a few weeks back, we were there and we were in their booth and we could show our technology and. For people following SmolTAK, they have perhaps seen the video where some of our employees, we have one employee over there, and another one was traveling there. We're interviewing ITRI. ITRI is a very big, or not a very big, but a prominent and strong player in the semiconductor market. It's the Industrial Technology and Research Institute of Taiwan.
Correct.
And can you tell us a bit more about the partnership with ITRI and what it means for us?
You're right, and they are very important for us for multitudes of reasons. So, and this partnership has come to a new stage since summer when we signed this 2 years agreement with them. Yeah. So, and the agreement defines 2 collaboration paths that will continue in parallel. One is the technology platform that we are going to use for Gen 1 fabrication. Yeah. So Gen 1 is being fabricated there, and this wafer just came from Taiwan, is one of the wafers that we are going to do further processing and dice and do measurement here, is a Gen 1 wafer. And the other collaboration that we are doing with them, of course, is the pilot line. Yeah. So as part of getting ready for low volume production, we need to make sure that we have the capability to address maybe not millions of capacitor a day, but maybe millions of capacitor a year. And that's where we are working on with ITRI. And they have experience with such setups. They have done that with others. And within that pilot line, we have secured the space for our PCVD tool to be installed and brought up there. It's not an easy process. It will take time. There's a lot of things you need to think about that before in full integration. But these are the things we are working on. And the fact that they chose us to attend Semicon Taiwan together with them, I think shows that they trust in our technology. And they are also preparing for hitting the market with us. I know they have the head of the group that we are working with has allocated resources and new investments for new equipments. Yep. For our technology development. So I think I would say it's very strong and very promising.
Yeah, and I suspect also now going to the market, most of our possible customers or potential customers are Asian companies, some Taiwanese, some Korean, Japanese, and so on. And of course, having ITRI as a technology partner in development and also early production gives them comfort, and it's an external validation for us. So it will probably help us there as well.
Exactly. Yeah. Exactly. Yeah.
Very good. So we collaborate with them, and then we also collaborate with YAGEO, and we have been doing work together with YAGEO and the US subsidiary Kemet for a while. What can you talk about that? What does it mean for us?
No, we never stopped working with them, and we continued our collaboration since many years ago. You know, with of course we didn't start this joint development that we had envisioned, but we continued with them. We still meet them on a monthly basis. We have a very strong technical collaboration between my team and Kemet's team. A very good example is what we did over the summer. One of the key KPIs of our capacitor is the parasitic inductance. And with everybody, anyone that we talk to, any potential customer, they say that this has to be very low, typically below 5 picohenry. And the problem is that our capacitor has such a low inductance that we cannot measure it here in the lab. And so it was very difficult for us to provide any numbers. So we worked together with the YAGEO team, with Kemet's team, and they have experienced experts who could help us to simulate, have the structure of Gen 1 and calculate and simulate the parasitic inductance, which we turned out to be around 1 picohenry, which is very, very good. I don't think anybody else can offer such low parasitic inductance. So that's a very good example of collaboration we have had. And of course, we are working very closely on the reliability side, and we hope that we could send very soon the samples to them so we could reproduce the good results we had at the SmolTAK with the reliability test at 85 degrees. We could reproduce that at the YAGEO.
Yeah. So they basically offer their equipment and expertise to help us out in this early phase.
Yeah.
Excellent. And then we have talked a lot about generation 1. If we move beyond generation 1, what do you see as our next step there?
Yeah, I think we will continue the development that we're doing. We also had an excellent investment that after 2 years of work now is in place. That is our new ALD system that significantly will accelerate our development, because previously we relied on external partners to do this key step for us, but now we could do it ourselves. So we could really produce new samples a lot faster than sending it somewhere else and staying in the queue, doing deposition and coming back. Also, it has an impact on the IP side. We will own the IP on that side as well, on the ALD side as well. So it's very important. And earlier in our conversation, I referred to aspect ratio, and 50 nanometer wide, 5 micrometer tall translates to roughly 100. And we are not going to stay there. We are going to increase the length of the fibers and have even higher aspect ratio. We already can produce very good fibers, tens of micrometers. So that's not the bottleneck. The bottleneck is to make sure that we have a conformal coating of very thin layer of dielectric, which is done with ALD over the entire forest. And that's the challenge. And that's what we are going to work on step by step after Gen 1. Increasing capacitance density and innovating around dielectric, and getting lower ESR, lower ESL, lower leakage, and higher capacitance density.
Yeah, and I know that you've been working with several ALD suppliers or partners before, and you have had very varying results. So
correct.
The hope, I understand now, is that having a machine on our own, there are lots of tweaks and settings that we can keep as our proprietary settings, and that will help the work in addition to the logistics of shipping things back and forth.
I think that will make a major impact in 2026. Once we have the tool is going to be operational any day now, and then we need a little bit of time to develop our own recipes, which takes maybe a month or two. And then next year, we are going to see the impact of that. And this year, we have, for example, we have a platform where we make this CNF-MIM capacitors, very simple ones, in a very fast and iterative fashion, so we could test new ideas. We had 12 of those iterations in 2025. We think we can double this up in 2026. So I think time to market is essential. And this tool is very important, helping us reduce that time.
Yeah, very good. So if we then look further forward, next 5 years, so where do we see Smoltek's technology in 5 years' time, let's say?
Yeah, I think difficult to predict the future, but I think in the next 5 years, we will certainly, the first step is just to show our capacitor as a discrete capacitor will work, right? So just somebody can get it mounted on a PCB, SMD component, and use it.
As a standalone discrete.
Discrete component. But that's only the first step. we want to work on more advanced packaging alternatives, and that require working not only on the front end of line that we usually call it the capacitor itself, but also how we package it, how we integrate it with interposers, silicon interposers, with glass interposers, with PCBs. And we're already looking into that. We are already actually in a European project. We have in a European project application. And if it goes through, that really enables us to work exactly on this topic, to see that how we could use our technology with more advanced packaging, what sort of changes we have to make to that. And of course, we have other ideas with this. We also can, apart from embedding our capacitor into these structures, we could also grow our fibers eventually directly on the active component, on the CMOS chip, on the GPUs, to say, on the back end of line of the GPU. That's as close as integration you could get.
Yeah.
And we have shown previously that we have fundamentally we have growth processes that are fundamentally CMOS compatible. We had a project in the last years that we successfully concluded with a French company that wanted to grow carbon nanofibers directly on image sensors. And we showed that we could do that without damaging the image sensor itself. So these are the things that I expect to happen in the next 5 years. First, hopefully successfully launching our product as a discrete component, and then move towards more advanced integration.
And this concept. EU project, I've read somewhere that the EU Chip Act, it's financed by something like 34 billion euros or so. So it's quite big money going into European semiconductor industry right now.
Correct.
And we are part of a consortium for chiplets. Right?
Yeah, that's true. We have applied together with more than 30 other partners in Europe. We have submitted that as part of CHIPS. It's called CHIPS European Chip Act.
Yeah.
I think the project itself, the budget of the project is more than 400 million kroner. And we, in that project specifically, we will develop advanced integration and work on the power distribution network side. This chiplet idea is, I don't know how much you're familiar with that. So when you have, let's say, a CPU, it has a brain part, it has a memory part, it has a control part. These are all on one single chip. So if you want to innovate, you have to redo the whole thing. Yeah. The other idea is to separate them into smaller chiplets. Yeah. So if you want to improve the memory area or your Bluetooth area or your connectivity area, you don't need to redesign the whole thing. Yeah. But then these chips have to work seamlessly with each other. These chiplets have to work. Yeah. And also, you need to address the power distribution. And now you have a capacitor that we make, which is a chiplet, which is a piece of silicon that matches this ecosystem very well. And this is what we are working. That's not the only...
But it's a trend in the semiconductor industry, chiplet. So, so we're following into that trend. Yeah.
And that's not the only European project that we are tapping into. We actually got from Infrachip over the summer, we got a good funding we got an approval and we received money from EU to do transmission electron microscopy of our chips in Europe. So these sort of imaging cost a lot of money. Yeah. And we wanted to check the quality of our ALD layers on top of the fibers. And we got that for free, so to say, which is, I think, very good, very important for our development.
Yeah. Very good, and I think there is one big question in the industry. This is a bonus question, I think. But if you look next 5-10 years, do you think Moore's law will continue?
Yeah, I think that's a very difficult question. We have already seen that it's slowed down. Yeah. We are not doubling up or making the measuring the improvements for this every year or every 18 months. So the advancement in semiconductor industry, as you know now, comes a lot from advanced packaging stuff. The way you integrate your memory, you stack up your memory, and combine it with your CPU in a different way. And I think these are the sort of improvements you see. We are already at 18 angstrom.
Yeah. So it becomes harder and harder.
Yeah,
that's for sure.
It becomes harder and harder. Of course, there are ideas like graphene replacing that. There are ideas of other 2D materials. These are all fantastic ideas, but I think they still have a long way to go.
But if Moore's law is to continue, perhaps new materials are needed.
Yeah, there is a company in Lund now working on, this nanowires, how you could make better or higher frequency transistors with nanowires. And, these new materials, of course, will play a role in continuing, not maybe the classical Moore's law, but, in different ways, making sure these improvements, these gradual improvements will continue in different ways.
Yeah. Thank you very much. This was an excellent overview of the technology and all the interesting things that we have in pipeline here.
So, yeah, thanks. It was great talking to you, and hope we continue this tradition.
Yeah. Thank you.
Thank you. Take care.